Awesome, it's working.
Yep. Hi, everyone. Okay.
All right, feel free to get started whenever you feel like it.
Okay. I can share my screen and just get this. Yeah. Hang on, I gotta figure out which one.
Maybe if you want me to hop in here, I think I have the slides ready too.
I'm just trying to figure out which window this actually ends up being. All right. I don't know if I'm sharing the right window or not.
Jason, do you want me to try it on my side, and then you could just cue me on the slides, or
I have it. Like I have a window shared.
It's my first time using this this platform too, so. May not be the most help here.
Okay. Okay, we'll stop that. Add from. Oh, all right.
I think that's my screen.
It is.
Do you
Perfect.
Do you want me just to go to the beginning and you can cue me through them?
Yeah, let's do that.
Have the most up-to-date slides. Take it away, Jason.
All right. So, hello everyone, and thank you to Ignition Hacks for hosting us. And we are here to give you an introduction to machine learning and artificial intelligence. My name is Jason, and I'm here with my colleague Josh. So let's get at it. So first, a few caveats. This is an intro to machine learning and AI. We're going to be talking about a lot of topics and not a lot of time. Secondly, we're knowledgeable in machine learning and AI, but these are huge topics and they're huge fields of study. So we have experience, but I don't consider myself an expert. I won't speak for Josh, but
I consider myself less of an expert than yourself. So,
so there you go. And we will do a demo at the end. It will be live. We've made the proper sacrifices to the live demo gods, but we'll see how it goes. Okay, next slide. Okay, so first let's talk a bit about artificial intelligence. Next slide, please. All right. So in general, we can group artificial intelligence into 4 main categories. There are others that we can add to it, but these 4 are what I feel kind of the core. So as we go from left to right in the boxes, we go from a bit more practical and more in use to a little bit more hypothetical and in theory. So starting on the right, we have reactive AI. This type of AI does not use past experience to come to decisions in the present. A good example of this is IBM's Deep Blue. This was a chess playing robot that only looked at the board state and figured out what the best move to make was, and then you would make that move, and that would be how it played chess. Next, we have limited memory. So, like the name suggests, it uses the past to make decisions about the present. It's also limited memory, so we have self-driving cars would fall into this category, and in general, machine learning would also fall into this category as we train it on data, and it uses that memory of that model to make its decisions. Then we have theory of mind. This we're starting to get into the less concrete and the more theoretical. We do have this tries to understand and kind of mimic human sentiments and human emotion. In the 90s, there was a product called Kismet that tried to do this. You can look it up on Wikipedia. It looks kind of like a Furby. It's kind of nightmare inducing, but it's there. It didn't have an easy time doing this. More recently, we have Sophia from Hanson Robotics. That one has she has cameras in her eyes, so it's a lot easier for her to kind of track your movements, kind of mimic your expressions, and kind of interact with you on a little bit more of a natural level. And then finally, we have self-awareness, the thing that science fiction writers have been using to keep themselves in jobs for years. It's kind of the the AI is alive. It's purely theoretical at the moment, but that is kind of, I guess, the goal. So before we get into machine learning itself, which is what I'm sure everybody's here to see, I'd like to take a brief look at a specific type of AI. Go to the next slide, please. So this is a belief desire intent AI, or a BDI. At a really high level, this framework allows an agent to reason. It has a reasoning cycle, which is what we have as the interpreter. Well, as everything in that gray box is part of that cycle. It allows this agent to decide what to do and what plans to take to achieve its goals. So over on the left, we have the environment, and this agent will receive information from that environment. These perceptions or percepts can modify the goals that this agent has, and then these percepts will also be stored within the agent as beliefs. So this could be uh, beliefs about its environment, about what what exists, what doesn't exist, things it knows about itself, whatever. So these beliefs, along with knowledge of the goals that it has, and the goals that it wants to attain, and the plans that it has, this will cause it to come up with the best plan for the time, which it will then execute on as a series of intentions. And this execution will happen as either actions, which will reflect back in the environment, or modification to its goals. So, kind of a simple example would be if you have a robot that's in a room, it could look around its environment. It could have the goal of getting out of the room, so it could see that there's a door, the door to its left. So, with the belief that there's a door to its left, there's some space. It would have a goal of getting towards that door. So, its plan would be, move towards the door. The intentions would then turn until I'm facing the door, move towards the door, and then that would reflect as changes in its environment, or changes its changes within the environment. It would then go to the door, try to open the door, maybe find the door was locked. So now it's change. Now it has a change in goals of where it's going to try to now unlock the door, so that it can also fulfill its goal of getting out. So then this will change, and it will keep going around and provide kind of a human-ish way of thinking about a problem or reasoning about a problem and solving it. Next slide, please. So now we're getting to the basics of machine learning. So next slide. So this section is going to be split up into a few sections. The first part is going to be is validating your data. How do you know that the data that you have is good, and how do you know that you have picked the right aspects or the right features to train on? So imagine for a moment that you're hired to design a system to combat self-checkout produce fraud. A grocery store has found that people put produce on the little self checkout. They put apples on there, and then they ring them up as bananas and walk on out, getting the apples for much cheaper than they should. So they say, oh, we're going to install a little camera on the on the machine that's going to look at the weigh scale, and we want to try to figure out what the produce is, so that, and then check to see if the person puts in the correct produce or not. So they give you this data set, and this data set contains a whole bunch of things. It contains things like the weight of produce, the size of the produce, the shape, the color, where the item was shipped from, the name of the farm that it was grown at, the shipping date of the produce, all sorts of other data points or features. Now, you probably don't want to use everything that you're given. Some of these data points might correlate very closely, like the weight and the size of produce. In general, the bigger the produce is, the more that it weighs. So these are correlated very closely. Um, some of it might be completely irrelevant. I can't imagine the name of the farm that produce is shipped from is going to be super important in trying to figure out what that produce is. So this step of kind of filtering out things that are, one, irrelevant, and two, are just kind of two things that are so closely intertwined as to effectively be one point of data. This is a very important aspect of machine learning. It's going to help you eliminate noise. It's going to make your model less complicated, and it's going to make your model more effective, as it's going to be able to look at the more relevant data. So on the screen, we have two graphs. On the left, let's say we have a distribution of weights of apples in red and watermelons in green. So in this case, your other left. In this case, thank you. In this case, we don't actually need machine learning to figure out what is what. We can put the item on the scale. If it's below a certain number, we know it's an apple. If it's above a certain number, we know it's a watermelon. Okay, so this is not really a problem that we need machine learning for. So on the right, we have, let's say, instead of apples and watermelons, we have apples and green peppers. So some apples are large, some green peppers are small, and they happen to have some overlap in weights, which is represented by this blue squiggle. That's the intersection of these two areas. So maybe machine learning, it can help us distinguish what's under this blue overlap. Uh, so in this case, we would want to use more data. Maybe we can use the color of the object. Apples are generally red, green peppers are generally green. So we could use this to also help. We could maybe use the size. In general, I expect that apples are smaller than peppers. So these are all other things that we can use to kind of get at this mixing of we're not exactly sure what it is. So next slide, please. So this kind of goes into there are a few types of error that exist in machine learning. Kind of what I feel is the most important is this indistinguishability error. This is an error that we try hard to eliminate but can't really eliminate, because if we eliminated it, then it would just be a normal software development problem. It wouldn't be a machine learning problem. So this is kind of inherent into machine learning because it's what we use machine learning for. Uh, in general, there's a bit of a trade-off between having too many features, so it makes your model a lot more complicated to train, and having not enough features. So you're going to get a lot more things that are classified incorrectly, like that previous graph. If all you had was weight, all the apples and peppers in that middle section, well, you're kind of flipping a coin as to whether or not it's an apple or a pepper. So then we have model error. This is if we use the wrong features. So if as well as using the weight of a produce, I'm also going to use the size, which earlier I kind of said might be kind of tightly correlated together, then this is not going to be as useful as maybe using the weight and the color, or the weight and the shape, or all three, or any other combination. So this is kind of we've used the wrong features. We haven't used significantly independent features. And then finally, we have the estimation error. This is how robust your data was. If in all my training of a classifier or a machine learning algorithm, if I've only ever used red apples, and then when I put it into production, somebody puts in a green apple, I can't expect my model to know what a green apple is if I've never shown it a green apple. Next slide, please. So we've kind of gotten an idea of how to validate that the data that we have is good, and what aspects of that data we want to use. So how do we train it? Um, if we take all the data that we have and we train our machine learning model on all the data that we have, and then we test it on that same data, we're going to get great results because we're just giving it more of the same stuff that it's already seen. It knows how to classify that very well. This is kind of like writing a program and then testing three easy things that are easy to test to go, oh yeah, everything works. We're good to go. It's not useful. So one of the easiest things that we can do is we can take all the data that we have and we can split some of it into training data and some of it into testing data. So we'll have two categories. The general rule of thumb is about 80% training data, 20% testing data. And we'll train on the data that we've set aside to train. And then that other 20% we can use to test the classifier or the machine learning algorithm to make sure that it actually does what we want it to do. And it's not just kind of randomly throwing things into categories. After that, we have what's called cross-validation, or M-fold cross-validation. So this is a bit like holdout testing, but instead of doing an 80-20 split, we're going to split data into M groups. So let's say 10 groups. We're going to train on all the groups minus one. So in this case, we're going to do 90% training and 10% test. And then we're going to keep repeating this over and over again, changing that test group. So we're going to effectively do this 10 times, changing the test data so that the algorithm has new data to test on every single time. So this is more robust than holdout testing because it lets you be a little bit more resilient to things like outliers. Maybe you have some really big apples and that just completely throws off your model. Or, maybe whoever wrote down all of this data got it wrong, and so they made, a mistake somewhere. They forgot some ones or whatever. So these are two kind of easy and simple ways to take data that you have and kind of make the most of it, making sure that you actually have a machine learning algorithm that works. The last thing that we have to take into account is class imbalance. This is if you have a lot of what we'll call hits versus misses. So I'll put my grocery store produce example aside for a moment, and let's say that I'm instead writing a classifier that's going to look for malware in a file system. I could probably get maybe, let's say, three files that are infected on my file system. But a file system can have millions of files. So your the data that you're provided is could potentially reflect millions of benign files and three infected files. So this is class imbalance, and if it's something that you have to deal with your project, there's a lot of resources out there. I would suggest kind of going. There's a lot of different ways to sample, ways to kind of make sure you have both classes. There's a lot of information out there, and that should be something that you would look into if that's a problem that you'll face. Next slide, please. And so finally, we have we have a good idea of the data that we're going to use. We have a good idea of how to use that data to train our model. We train our model, and now how do we know if our model is any good? So we can compare our model to other models, like other trained models, if we're trying to come up with a better model than what exists. Or at worst case, we can just compare it to some sort of random or pseudo-random model. And classical hypothesis testing, we could test against a null hypothesis. Is the model that we've trained, is that better than or significantly better than doing nothing? Is it significantly better than just randomly assigning data to categories and so on? We have Z tests, T tests. I think chi-squared is another test. These are all statistical methods of figuring out whether or not what we've done is better than what exists out there or better than random. Again, this is stuff that if you're interested in, you should. The math gets pretty hard or pretty gnarly, so it's something you should look into if you're interested in that. Uh, then we also have measures of accuracy. We have a lot of measures of accuracy when it comes to machine learning. Some of the more common ones: how often are we correct? How many false positives did we generate? How many false negatives did we generate? Uh, these are good, but can't be taken on their own in a vacuum. If we go back to my malware example, if I'm expecting, let's say, 3 infected files out of 10 million benign files, my classifier can just mark everything as benign and have 99.9999% accuracy, which is great, but it's absolutely failed in its job at figuring out what files are malicious. So there's a lot of kind of looking at the various measures of accuracy that we have, seeing if they're okay, seeing if they're appropriate for the problem that we have, using the statistical testing to make sure that what we have is better than something else significantly. And it's not just, well, it's a little bit better, but that could just be the random data that we used. And then finally, we have this idea of, is it better to produce a false positive or a false negative? So if we go back to my grocery example, uh, if the model that I've trained incorrectly says that somebody has fraudulently put in the wrong produce, so I put an apple, I weigh an apple, I say it's an apple, but my machine learning algorithm says no, that's an avocado when it's not, and it goes and notifies security, and I go and walk out, and security stops me and searches my bag, that could have unintended consequences. I could go on Twitter and roast the grocery store for, searching my bag for no reason or whatever. But then on the other side, if my if I if I put an avocado on the scanner and I say it's an apple, and my algorithm says, yeah, that's an apple, and it lets me walk out no problem, then your grocery store is losing money, it's losing inventory, and then the grocery store is upset with me because my algorithm isn't working as intended. So you kind of have this fine line. Sometimes it doesn't matter. Sometimes you pick one, or you get some false positives, you get some false negatives, it's fine. But sometimes it really matters, and then you kind of have to tweak your model to go one way or the other. So that was kind of the brief intro to the theory behind machine learning. Josh is going to take it away to talk about the types of machine learning.
Yeah, thanks, Jason. So yeah, I'm going to be talking about the three major types of machine learning right now, which is supervised learning, unsupervised learning, and reinforcement learning. So we're going to start with supervised learning. So the basic idea here is that we have a large input data set, and we have a lot of data that we can actually use for training. So I like the fruit example Jason was talking about. Here it's like, maybe we have a ton of pictures of what apples look like, and that's what we're going to use to train our model. So that's the basic idea with supervised learning, is that you have an input data set to train with. Here's a couple of examples of different types of machine learning algorithms. So one of them is the support vector machines. And this one is kind of focused on delineating between different and drawing a line between two different data points. So if you kind of imagine a Cartesian plane, XY axis, and a bunch of points on it, we know where our clusters are, and we're trying to draw a line between them. So, on 2 dimensions like this, it would be a line, and we're trying to find a line that's the furthest away from any points to get the most differentiation possible. And if we get to more and more dimensions, it kind of starts becoming a hyperplane and stops being a line. But that's kind of the general idea, is you're dividing up the data. The nearest neighbors is another really common one. You might see referred to as KNN, which is K for a constant and NN for nearest neighbors. So this is basically a game where you have a bunch of points on a graph, and you're trying to figure out a new point and what that point that should belong to. So we kind of have our two clusters, and we're saying, well, this new point, let's compare it to all the nearest data points nearby it. And see which of its how many neighbors there are, and take the majority of those neighbors. So if it's take the closest 10 points, and if 8 of those 10 points are apples, then this new data point is probably an apple too. The next one I'm going to briefly talk about here is decision trees. So decision trees are a little bit different. They kind of just imagine kind of like a family tree or something. And it's basically a way of categorizing data. So I don't know, for example, maybe if you're looking to determine if you have a bunch of socioeconomic data, like maybe a census or something like that, and you're trying to estimate certain costs for like who's going to cost the most on the healthcare system, you might have a decision tree that is going to kind of break it down variable by variable, and then categorize categorize data points within that decision tree. So they might find that the very most important variable is age, and whether you're at the most important data point maybe is 70 years. So if you're over 70 years, then you go down this side of the tree. Otherwise, we go down this side of the tree. And then at each level, there's different variables and decisions that are made to break up the data. So the next one we're going to talk about now is unsupervised learning. So unsupervised learning, it's like kind of similar to the previous one. We actually don't have an input data set to label and to make sense of it. So we kind of just have a bunch of data, and without training it, we need the algorithms to decide what each data point represents and where the clusters are. So you kind of see here, there's 3 different forms of clustering. And the main goal of all clustering is to maximize the difference in between the clusters while minimizing the difference within the cluster. So, you want all your apples to kind of look the same, have very similar weights, but then you want the maximum differentiation between clusters. So, maybe pineapples weigh a lot more. So those are nice, two very distinct groups that we'd be able to make two very separate categories for. And then hopefully the things within the category are very similar. So, hopefully all the apples are within a very tight range. So that's kind of overall to clustering. The three types I'm going to talk about here. The first one's k-mean. So I'm actually going to be doing a demo that's going to be using this algorithm. And this one is basically, it picks a bunch of data, picks a bunch of possible centroids for these different clusters, and then juggles those centroids around until it finds something that fits the data set as best as it can. And then that's how you kind of end up with your clusters. The spectral clustering uses eigenvalues and like linear algebra, and tries to make the clusters as similar as possible. And hierarchical, there's kind of two forms of it. So it can either go top down or bottom up. So with top down, you're kind of starting with all the data points are part of one cluster, and then you try to find the best way to break that into two different groups. Then once you have those two, you continue to break it down and down and down. So kind of top down. The other approach is bottom up. And that one, everyone starts out in their own data group, and then you start grouping them together where it makes sense and keep grouping up and up and up until you have the number of clusters that you're looking for. So the last type of learning I want to talk about today was reinforcement learning. So this is a little different than the first two again. And with this one, you need to be able to come up with a way of evaluating your algorithm at every step that it takes. So I would like to think of this one as like almost kind of a Marco Polo game where you got someone blindfolded and someone saying like warmer, colder, and you're trying to find an object in a room or something. So the blind thing is the AI algorithm, and it's trying to like go around trying to figure out what it needs to do, and it needs to get feedback of knowing whether it's doing a good job or not. So that's kind of the warmer, colder part of it. The common example here is a maze. So if you imagine trying to navigate through a maze, you might be able to come up with a function that says, okay, let's just calculate the distance from where you are to the exit from the maze, and we'll feed that back as the feedback for this one. So if you're getting closer to the exit, that's a good sign your algorithm is doing well. If you're getting further away from it, then your algorithm isn't doing well. Now, obviously, with a maze, you might have to get further away to solve the maze at some point, but that's part of the nature of these algorithms as well. So that kind of warmer, colder value that we're feeding back to it can be referred to as the Q value, and that's where we get Q learning from, where we're actually giving it feedback as we go through this process. And there's a bunch of different types of Q learning, which include deep Q learning, and that one is actually using a neural network with the process as well. So I think we'll go right on to the main takeaways here. So there's one of the big things here is there's no free lunch when it comes to machine learning algorithms. So there's no like one algorithm that you need that'll just work on all your use cases. You actually need to kind of understand the different algorithms. You need to really understand your data and understand what your goals of the analysis are, and then try to find an algorithm that's going to suit you the best. And then even once you choose the algorithm, all of them are going to have a ton of different options you could choose within them, like the number of clusters you want, the number of nearest neighbors that you're going to be searching with. There's a ton of different parameters, and you have to kind of consider each one of those as well with your data. So there's a lot of kind of thought that has to go into one of these, into coming up with a good analysis using machine learning. And that's something you have to keep in mind when you're getting into it. The next thing is feature selection. So this is kind of what Jason was referring to here. Like knowing the name of the farmer that produced the produce is probably not going to help you decide, whether it's an apple or a pineapple. But other data might be helpful, like maybe knowing how far it came to arrive at the grocery store might actually be a helpful piece of data, because maybe apples tend to be sourced more locally, where kiwis and mangoes tend to be coming from afar. So you have to be very conscious in which features you select and making sure you don't just give it everything, because if you just give it everything, it's going to find a correlation on one of the fields just by circumstance and by chance. So you want to make sure you're giving good data. I remember one of the things my prof always used to say was like garbage in, garbage out. So if you give your data garbage, if you give your algorithm garbage data, it's going to come up with garbage results. And the last one is don't get stuck in the weeds of accuracy. So this one is kind of just Jason referring to it a little bit earlier as well. There's a lot of different metrics that you could use when calculating how good an algorithm is. And there's such thing as overtraining an algorithm as well, where it's not actually producing helpful results, but is going to show very high accuracies. So you just have to be careful in how you analyze, and just because you have a high accuracy doesn't mean your algorithm is necessarily doing the job well. Yeah, I think that's about it. Jason, do you want to add anything to the slide before we move into the demos?
Nope. No, I think it's time to try the demo.
Yeah, cool. So yeah, demo time. So we each came up with a little bit of a demo. I'm kind of focusing on something that's a bit more, that falls within the unsupervised. And I'm using the data set at the top here, the California housing prices. So let me just see if I could switch my screen sharing right now. All right, Jason, I guess actually you're not on YouTube either. I'm just going to assume this is working and move forward. So I actually can't see the YouTube comments right now either. So I'm sorry if there's questions there that we're not getting at. So this is a Jupyter Notebooks. I'm sure some of you are familiar with this one already, but basically we're just running a bunch of Python code cell by cell. And if you guys need any help setting up your own Jupyter Notebooks, feel free to reach out to me on the Discord channel under Security Communications Establishment. So anyway, first cell here we have is just installing all the libraries that I'm going to be using here. I think the main one to note here is sklearn. That's the one that's actually doing the k-means analysis. So going down here, here I'm actually loading in my data and setting my target field. So I'm choosing to target housing median age. And I could be targeting multiple fields here. I'm choosing just to focus on one just to make the analysis a bit more simple. But you know, if we're doing a machine learning algorithm, we could throw a bunch of different things at it. It doesn't have to be 2-dimensional, 3-dimensional, it could be nth dimensional. So here we're just taking a quick look at the data, reading it in. So I'm targeting this field, but I'm also considering longitude and latitude to make this a spatial analysis as well, because that's my specialty, is all things GIS and spatial. So then we're going to take just a quick look at the scatter plot to get a sense of the data. So here we are with the housing median age, and you see kind of the low values are around 10 and the high values are around 50. So this is kind of just a quick example of why you should really understand your data. I originally thought that this was referring to the age of the people in the house, but seeing the 10 here, I could say, okay, well, this is probably actually referring to the age of the house itself, because there's probably not going to be a household that's has a median age of 10. So this goes to show you really need to be able to know your data and know what you're dealing with, because it could get you at any point in time. So here we're actually starting to pre-process the data. So what we're doing here is we're normalizing it. So we have different fields that have different magnitudes. So for example, if we're talking demographics, there might be a field for the number of cars a household owns, and then the household income. So, you know, the household income could be like $100,000 or something like that. And that's obviously going to be a lot larger than the number of cars, which might be like 1 or 2. So by normalizing it, we kind of get everything within this same range, so we can start comparing them evenly, just because, you know, household income is such a larger number than number of cars doesn't mean it's necessarily more important. So from there, we go into the actual k-means analysis. So here I'm setting the number of clusters to 3 and some other variables here too. I end up playing a bit with the number of clusters in this analysis, but not these ones. Again, you have to kind of consider all the variables going into it and all the parameters going into the analysis as well. So this one, we're going to do a little box plot of it. And here we can see our 3 clusters. So we're showing just one variable along the side here being our target variable, which was household median age. And I also included latitude and longitude in this analysis as well. So this is just showing the differentiation between one variable. But here you can kind of see the clusters are relatively short. And then there's a decent amount of separation between them. Though you can see there's some overlaps in the box plot tails here. So this isn't a perfect differentiation, but we still have 3 pretty distinct groups here, which is a good sign. Now let's take a look at that on a map. So we can see here, we're starting to see like more localized clusters, which is good. This is what we're trying to find. So maybe we're trying to find like, neighborhoods where the houses are older. So maybe we could start up a new renovations company in one of these areas. So we can see here, we're starting to see clusters, which is good. Maybe these are probably cities where the houses are a bit older. I kind of see some lines here going on too. Maybe these are highways where communities have been around for a bit longer. And then we see a lot of lighter colors in the outskirts. So maybe this is where the newer developments are happening. So one of the scores that we can look at here is the silhouette score. This can range from -1 to 1, and it's just saying kind of how much separation are we getting between the clusters. So you guys could take a little bit of a look at that later, but we're getting 0.5, so it's above 0. That's a good sign. But maybe we can play around with the parameters a bit and see if we can get this a bit higher as well. One of the things I wanted to look at here is just the number, choosing the number of clusters. So that's one of it's the first parameter they're looking for in the k-means analysis. And I figured we'd just try it with a couple of different ones here. I ran it for a bunch. I only decided showing one of them with a larger amount of clusters. So here we can see there's 7 clusters here, and it's looking pretty noisy. Like it's a bit harder to see patterns here. And we're also getting like pretty close to how our original map looked of just like mapping the variable of median household age. So I don't think I want to use this for my analysis just because it's kind of getting a bit too complicated. I'd rather keep it a fewer amounts of clusters. We're not overtraining it so much then, and it's easier to understand. So so from here, I actually want to start trying to create a map. So one of the things I want to do when creating a map is be able to interpret all the area on the map. So here this isn't even a map, this is just a plot where we're plotting latitude and longitude, so it's a flat projection. But let's say, we want to know what's going on here and what's happening over here, what's happening between the points essentially. So we're going to do interpolation to basically calculate the values so that we get a full map coverage of this. Of our classification. So we're a little tight on time, so I'm going to skip this one particular example, but this is kind of a more generalized one, and this is one applied to our data. So here we have our sample points, and we can see there's 3 colors here, so those are the representing the 3 clusters that we have created. And here we have a couple of different methods. Again, these are machine learning methods that are used for calculating calculating a grid essentially, so filling in the points between all the data. So both of these two, both linear and cubic, kind of assume that our data is scalable. So our clusters kind of are right now because we saw from our box plot up here that 1 is more than 0 and 2 is more than 1. So there's kind of like an upward trajectory here. So it kind of works out with this data set that something in between the two of them would represent a point in between these 2 clusters, which makes sense, but that isn't always the case. So for example, if our clusters were, let's say, or our data points represented like job categories, so maybe we have mechanic representing number 1, programmer representing number 2, and a doctor representing number 3. halfway between, if we calculate the average between 1 and 3, it would be 2, but halfway between a mechanic and a doctor isn't necessarily a programmer. It just doesn't make sense. So this is another point where you have to be careful in the data, that which data you're using and understanding how to apply that data. So the one I'd want to use here is nearest neighbor. So this is basically just applying, for every point on the map, it's saying, okay, what's the closest known point, and then just assign the value for that particular pixel to the closest value. So in that sense, we get a full coverage of our map, which is great. So now we actually kind of have a look at neighborhoods. So we could say, okay, well, maybe these yellow clusters represent actual neighborhoods, and maybe they're even delineated. And maybe these are the original neighborhoods within the city where the older houses are. So this is something that we can actually start using for analysis and even finding picking a location for a new renovation company. Final thing I want to show here is just a heat map. So we're just taking that those values and putting them on an actual map, and we can actually start to look in here and say, okay, well, look, there's a hot spot happening right here in the middle of Los Angeles. So, you know what, that kind of makes sense to me. I bet that's maybe where some of the older houses exist within Los Angeles. So maybe that's actually where we want to start up our renovation company. Yeah, so that kind of sums up what I wanted to talk about for this example. So I'm going to pass it back to Jason.
All right. Now I'm going to try to share my screen, and we'll see if it works. All right, well, I did say that live demos were tricky, and
We didn't sacrifice enough to the live demo guys.
I obviously didn't. Let's see, it is not doing anything right now. Okay, let's close a few things and make my life a little bit more simple. And let's see. Yeah, share screen. Did you have to do anything particular?
No, it was just the present button at the bottom of the screen there thing, and
share screen
then,
gives me some tips.
Share screen. Yeah, I clicked through that, and then I picked a window and it started working.
I'm not getting.
Are you using what browser are you using?
Oh, I'm using Firefox.
Yeah, I'm using Edge, so maybe it's a
all right
thing. Do you want me to? I have another thing. I skipped over one of those cells. Do you want me to just go back to that and speak to a bit, Jason?
Yeah, I'm going to try to reconnect using Edge.
All right.
We'll see how that works. So I'll be right back.
All right, well, thanks for your patience, guys. Let me just see if I could talk about that one last thing that I skipped over. Okay, so that was this one over here. So this is just an example I pulled online, but I thought it was really good. So we actually, one of the things I want to pull attention to here is there's a function here. It's just a bunch of trigonometry, but it's a function. It's always going to produce the same results. So that function is shown in the first screen, in the first of these plots here, and that's the underlying color here. So nice looking trigonomic function, pretty star. I like it. And we have a bunch of random points dropped on that map. So what's actually happening here is those random points are going to grab the value that associated with them from the function. So essentially they're going to grab the value from the image underneath them. And then we're going to use those points for our further analysis here. So what you can kind of see here is we're trying to get back to our original function using machine learning. So once we have all the values on those points, we can actually start applying functions to kind of guess what the values are in between those points. For example, I like this area right here. I think you guys can see my cursor. I hope so. Kind of right underneath the star here, there's an empty space with not many points in it. So one of the things we're trying to do here, and all the feature ones, is interpolate the value in that missing area where we don't have any data. Because again, we're not using the function, we're just using the points. So you can see right here in the nearest, the kind of nearest neighbor analysis, we're just grabbing whatever point is closest, which is probably the point that's kind of at the top of this empty area. So you can kind of see the nearest neighbor has this big blob going down right underneath the middle yellowish point. And that's kind of, it's trying to do its best to fill in that empty space. So it's not great, but again, as I was talking about earlier, there's times when the nearest neighbor is the one that we want to use because we have categorical data and not scalable data. So that's the nearest neighbor. Then we kind of get into some more mathematical approaches here. So we have a linear approach and a cubic approach. So you can see the linear, we're getting much closer to what our results our original underlying function was, but still not quite perfect. And as we start to get more and more complex in the math that we're kind of allowing this thing to do, we get closer and closer to our original function. So this is just I don't know, I thought it was a cool short example just showing how interpolation works and the advantages and disadvantages of these different models. Jason, you're back. Excellent.
I am. So we'll see if I can share now, and it's window. Oh, this is so much nicer than. All right, let's see if. Oh, all right. All right. So Josh had an example of unsupervised learning. I am giving a few examples of. Josh did unsupervised learning. I'm going to give a few examples of supervised learning. That doing a little bit better now. Okay, so I took it. It's very hard to get malware data in an open source in an open source format, and I wanted to get something that was a little bit more malware oriented because while I work for CSE, I actually am at the Canadian Centre for Cybersecurity. So this is a little bit more in my wheelhouse. So what I ended up doing was I found some Internet of Things data. It was packet captures, and they labeled it with different Internet of Things labels. So I think there was some baby monitors. There was one of them was automated lights, temperature sensor. I think there was a water sensor. So I just took all those labels and just renamed them. So the original data set is in the presentation. I just went and changed all the labels to make it fit what I wanted to talk about because it was kind of hard to find it otherwise. So this is Jupyter Hub. This is a lot of what a lot of people end up using. Now, Josh kind of cheated and didn't actually run any of his. So I'm really tempting fate, and I'm going to actually run all of these. And well, we'll see what happens. So here we're just loading some data. So we've got some training data. Because our training data actually has the data as well as the labels, we're going to strip off the labels. We're going to put them into their own data frame, and then we're going to drop the labels from our training data. So we can see that we have 900 rows and we have 297 columns. So that's 297 different features that's probably too many, so we're going to pare some of that down. And then our labels, 900 rows in one column. That's as expected. So now just a little bit of Python plotting magic to show. So here's the breakdown of our training data that we have. We've got 100 samples each of, and renamed from whatever they were renamed into just various different types of malware. So we're going to do the same thing with our test data. It is completely coincidental that we also have 900 rows of test data. Normally you probably won't, but that's what I downloaded and that's what I'm using. Then again, a little bit of Python manipulation and plotting, and so we see our test data is also 100 of each of the different types. So sklearn, I'm also using sklearn. Sklearn has this correlation function, which will take all of your columns and then it'll compare them to all the other columns. So you're going to get a big matrix with all of your columns across the top, all of your columns down the side, and then so your diagonal is going to end up just being 1 because they're going to be the matchup of each column, and a column will correlate with itself perfectly because that's just how it goes. So this ends up just being a little bit of manipulation. We're going to do some manipulation. We're going to mark any columns that are more than 80% correlated. We're going to mark them to be dropped, and we're going to keep everything that's less than 80% correlated. And that's just going to be kind of what we do. This is something that, as data scientists or machine learning people, you're going to have to kind of figure out yourself. That it's a little bit of playing around. So there we go. We're going to drop 131 columns from our data. So we're just going to actually drop the data, and we're just going to show that we now have 900 rows in our testing and our training, and 166 columns. So hopefully 166 plus 131 is 297. So now we get into the actual classification. So I'm going to do all the classifications, all the machine learning classifications that Josh talked about in machine learning plus neural networks, because everybody loves a neural network nowadays. So we're doing the same thing over and over again. We're creating a classifier. We're going to use this classifier. We're going to do a fit on it, which is the actual training of our algorithm. So we're taking our training data and we're taking our labels. And so we're going, here's the training data, here's what it is. Come up with some sort of classification for it. Then after we do that, we can then run the predict function, giving our test data. So now we're going, okay, you've got your model. Here's a bunch of other data. You tell me what it is. I already know what it is because I've got a list of the labels, but now I want you to tell me what you think it is. Then sklearn also has this metrics library, which will give you what's called a classification report. So I will take my labels, the ones that I got from the data set. These are what I know they are because that's what I've been told they are. I'll compare it to what the algorithm thinks they are, and it will give me a little report. So here's a report that we get for support vector machines. So we got a few terms here that I can quickly define. The accuracy, as one would expect, this is the number of correct predictions that are divided by all of the predictions. So, like I said, if you have a large class imbalance, you could really cheat this value and give yourself a 99.9% accuracy, but it's not really going to mean anything. We have the precision. So the precision is the correct predictions of that class divided by all of the predictions of that class. So how many times we got it correct divided by how many times we thought that was the class. So related to accuracy, but a slight flavor difference. And then we have the recall. So the recall is the correct predictions of that class divided by all of the occurrences of that class. So it's the number of times we got it right divided by the number of times it was actually that class. So like again, right? You're getting a lot of different flavors of measure of accuracy. They're all kind of subtly different and giving you a slightly different idea of what's going on. The F1 score is it's an average. It's some sort of average of these two. I'm not exactly sure. The closer to one it is, the better it is. So then the support the count of that classification that existed. So we can see that there's a lot of labels that our classifier hasn't even figured. So maybe not the best classifier to use. So now k nearest neighbors. We can see that this one looks a little bit better. Decision tree. We're getting at least less zeros. And then neural networks. We're getting a lot of zeros for that one. And so finally, we'll have a little bit more Python manipulation, and we can just kind of see the precision, the recall, and the F1 score of all four of these classifiers. So it is important to understand that these four classifiers I just got out of the box. I did no messing around with their parameters. I did no trying to figure out which would be better for what, right? It was just here's four default classifiers that I'm going to just throw at this. So it's not a super fair look at these. It's more just kind of a here's how you can use them. Also, similarly, we have 9 different categories that these things could be. So we're expecting to see a lot less accuracy. Consider the average of a multiple choice test versus a true false test. So that's kind of the long and the short of that. So you have a few ideas on how to use things, different classifiers that you can use, whether or not they're the same. Like Josh said, there's no free lunch. You kind of have to use a bunch of these, or even maybe just do a lot of the crazy math behind it to figure out if you can mathematically figure out which one's better. So we ran a little bit over, but I do have the YouTube live open. So there are a few questions. So I figured we could ask and answer these questions, and then you guys can get back to your projects. All right. Well, this one's not a question. I wonder what Linux distro CSE uses for cybersecurity. Well, you're going to have to get a job and find out.
All of them.
Do neural networks fall under the category of reinforcement learning? I can answer this one.
Yeah, you'd probably be better with it.
In general, actually, I'm not 100% sure. There are a lot of neural networks. Neural networks are actually a pretty old technology that we just never had the ability to run. The neural networks get very complicated and very big with how deep they get. And so it's only been relatively recently that we've actually had the processing power to run them. And there's a lot of different types. In general, it's mostly supervised learning, but I would not be surprised for somebody. I don't want to say no, it's only supervised learning, and somebody pull out some weird obscure one that goes, oh well, no, you can, and that's not to say that we can't use multiple classifiers together, right? Josh mentioned the deep Q learning, which was Q learning plus a neural network. So you can mix and match a lot of these, and that's what a lot of these big a lot of what of these big machine learning algorithms do is they take a whole bunch of them, they all classify them, and then they go through another neural net or another machine learning language, which then classifies the classifications and kind of gets like, this one has, I think it's this one more than this one. So you can really get yourself get yourself lost in the sauce.
Yeah.
Would you say that improving on Kaggle works towards becoming a data scientist? If not, what's the best way to become a data scientist?
Love this question. Yeah, I guess I used to work. I mean, Jason, you might be more present in it now, but I used to do some work kind of in the data science area. And I think I think you're definitely on the right path. Just trying to gain experience wherever you can, and I think especially taking advantage of any co-ops you can is super key too. Just getting work experience at any company that does this kind of thing is super important. Yeah, just look for any company that has like analytics in the name. Usually we'll have a hire a bunch of data scientists. So yeah, I think you're on the right path though.
Yeah, and I would be surprised if universities don't have data science classes at least, if not just straight up data science programs that you could go and do. I mean, also it always looks nice on resumes if you don't have a lot of experience in the area that you want to go in. Getting experience, like improving on some of these works probably looks good and puts your resume a little bit higher than somebody else. So I don't think it would hurt. Also, what's the best way to learn / improve on EDAs? I'm not a data scientist, so I don't actually know what an EDA is.
Yeah, I'm in the same boat.
Okay. Sorry. And if you want to, you can DM us afterwards, and we can answer in our chat or something. If yeah, sorry. Like I said at the beginning, we're not experts in the field, so some of these terms go a little bit above our heads sometimes. Will these examples and slides be posted? And then do you mind sharing the slideshow? Yeah. I was under the impression they would be posted, but we can definitely make them available.
Yeah, your lovely host could tell us where to put them, and then we'll put them there and make sure you guys have access to it.
Yeah. And then finally, why did you drop the features that are correlated to each other? Okay, I can answer this one. So, in general, if you have two features that are correlated very closely together, like let's say, size and weight, then it's not really two features. It's more one feature that you're looking at, or it might not even really be a good feature at all. In general, you want to maximize the number of independent features that you have, and you also want to try to get away with as few features as you possibly can, because the more features you have, I mean, you saw the difference between Josh's demo, where he had one feature that he was looking at and he could graph things for you, versus mine that had 190 odd features. I'm not generating you a 198-degree graph to show you that all these features. So That's kind of in general why you try to drop correlated features. Now, I mean, data science is not a science that is governed by rules and regulations, so there is a lot of room to be wishy-washy, to kind of wave your hands at things and go, well, you know, these two features might be correlated, but I want to keep them anyway because of reasons or whatever. So, don't take what don't take what I say as gospel, but that in general, these are good rules of thumbs. There's a lot of kind of playing with the data to see how you can make it say something interesting or something useful.
Yeah, I could even think of a better, like a different example to kind of prove your point of Jason is like if you have a timestamp in a file, and then you have a separate field that's like a human readable timestamp, and then a third field that's like the day of the week or something. They're all saying the same information, and if you include all three in the analysis, then you're kind of like triple weighting the time field, which might not even be relevant to your analysis anyway. So
that's a good
yeah.
point, actually. Yeah. Oh, EDA, exploratory data analysis. I'm sorry, I don't know. Like I say, I'm not a data scientist, and I'm kind of at a loss for how you would graphs and stuff. Yeah.
Yeah, I feel like I don't know. When I was doing more analysis work, I feel like data exploration was like a super integral part of it and something that you really can't skip. Like you really want to make sure that you understand the data before you move forward with it. Like in my example, I didn't understand the data well enough to even understand that like it was the age of the house, not the age of the members in the house. So like it's something that sometimes gets skipped over. And maybe this is what you're trying to get at, maybe not. But in a programming analysis, I feel like it's super important to spend a lot of time just exploring the data and just getting to understand it before you even try to do any analysis with it. Start, counting the sums of things, see if all the fields are populated throughout the whole thing. Check the domains of each field too, see if anyone has like a negative age or something like that. Then maybe the data's garbage. I think that data exploration is a super important part of the whole analysis process. Hopefully that gets at what you're trying to get at.
I think there's probably also a math component to it, and I mean, I know that there's a lot of like online stuff. Khan Academy has a lot of kind of great explanations and kind of showing you how to do things, and just teaching you. So that might also be a kind of go into some more of the statistical analysis and learn a little bit more than what we kind of glossed over, but also kind of pick some of that stuff that might be that you might find fun, I guess, or find interesting, and just kind of drill down into some of that. That's all of the questions that are queued up here.
Again, if you guys have any more questions, just shoot us up at the Discord. I'm checking it out throughout the weekend. So let us know if anything else comes up, or if you need any help setting up even a Jupyter notebook or whatever, just feel free to shoot me up and help you do that.
Yeah, and we will be on site tomorrow doing recruitment for CSE. So if you are interested, come on by. We'd love to have a chat. And I think that's everything for us. Thank you to Ignition Hacks for hosting this and allowing us to info dump our intro to machine learning and AI. I think got anything else, Josh?
No, summed it up great. Thanks, everyone.
Perfect.